Om Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh, Syallom, Namo Budaya, and good to see you all, guys. So, in this my presentation, I take chapter Tool Steel and High Speed Steel, and my name is Yudis Chrisantya, and I have my university code is 23055310623. And our lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia, MT M Eng. In this material is Metallurgy TM2301. I'm from Mechanical Engineering, Technical Faculty, Udayana University. In this my presentation, I take my reference is from the Metallurgy for Non-Metallurgy Seccond Edition, is edited by Arthur C. Reardon. And in this chapter, we have 7 sub-chapter is a brief history, modern alloy, work tool steel, effect of alloying and carbides on wearing resistance, heat treating high speed and tool steel, and powder metallurgy tool steel and cutting tool coating. And tool steel belong to a special category or steel alloy that have been developed to manufacture the tools, dies, and molds that shape, form, and cut other steel alloy. They are also used to process many non-ferrous metals, and in some cases non-metals, such as machinable ceramic and polymer. Go to the first sub-chapter is a brief history. The modern story of tool steel begins with Benjamin Huntsman, a clockmaker from Sheffield, England, who is credited with developing the crucible melting process in 1742. This process made it possible to produce cast steel with carbon levels that fell between those of cast iron and wrought iron. In the second subchapter, we have modern alloy. The many complex, highly alloyed tool steel and high-speed steel were developed in the early 20th century following the success of Taylor and White. In tool steel properties, modern tool steel are characterized by an exceptional combination of attainable hardness, red hardness, toughness, and wear resistance. Attainable hardness is the capability to reach a specific level of hardness through heat treatment. Individual tools, steel, and high-speed steel can be heat treated to achieve a wide range of hardness value that often exceed the hardness capability of other types of heat-treatable steel. In the red hardness, also referred to as hot hardness, is the capability to retain hardness at elevated temperature. And the toughness is ability to resist breakage, chipping, or cracking under impact loading. Toughness may be viewed as the opposite of breakage. And the wear resistance is the ability to resist the effect of abrasion and erosion normally encountered by contact and interaction with outside source. In the grade classification, there are presently more than 40 classifications of high-speed and tool steel alloys, according to the American Iron Steel Institute (AESI). When the compound by the number of domestic manufacturers, the total number of individual steel in these categories exceed 150. In the effect of alloying elements, the T-series alloy contain 12 to 20% W with chromium, vanadium, and cobalt as the other major alloying elements. The M series contains approximately 3.5 to 10.5% molybdenum with chromium, vanadium, tungsten, and cobalt as the other main alloying elements. And carbon is by far the most important of the alloying elements and is very tightly controlled in a silicon up to level approximately 100%. The influence of silicon on a high speed and tool steel is relative minor. In a manganese contributes to hardenability, but concentration are generally not high in high speed or tool steel because relatively minor increase in these alloying elements markedly increase the brittlest of the steel and the danger of cracking upon quenching. In a phosphorus has no known beneficial effect of any of primarily properties of high speed, and tool steel is normally present as a tram element in the scrap that is used to produce this steel. And the chromium is always present in high-speed steel in amount ranging from 3 to 5%. It is mainly responsible for improving the hardenability of these grades. And the tungsten in high-speed and tool steel is of vital importance. It is found in all T-type steel and in all but two of the M-type steel. M10 and M50 are the exceptions. And molybdenum serves as the main alloying element in the M-type grades of high-speed steel. It forms the same double carbide with iron and carbon as tungsten, but it has roughly half the atomic weight of tungsten. And vanadium was first added to high-speed and tool steel as scavengers to remove flake impurities and to reduce nitrogen levels in the melting operation. And the cobalt, the main effect of cobalt in high speed and tool steel is increased to red hardness, which increase the cutting efficiency when high cooling temperatures are encountered in the surface. So the temperature we can see in here, when they have a good and best temperature, they will have the best effect. And in a sulfur, in a normal concentration of 0.03% or less has no significant effect on the properties of tool steel, and the nitrogen is generally present in air melt grades in amounts varying from approximately 0.02 to 0.03%. Rope tool steel. In the hot work tool steel manufacturing operation involve punching, shearing, or forming of metals at high temperatures. Hot work steel in the group H have been developed to withstand the combination of heat, pressure, and abrasion associated with such operation. In the cold work tool steel, because they do not have the alloy content necessary to make them resistant to softening and elevate temperature, are restricted to applications that do not involve prolonged or repeat heating above other non-machining work tool steel grades. In addition to the hot and cold work steel described, shock resisting steel, alloy special purpose steel, mold steel, and water hardening steel are also used for non-machining application. So like in this table, list composition limits for this steel as well. And the effect of alloying and carbides on wearing resistance. The wear resistance of high-speed steel and tool steel is strongly dependent on the amount, type, size, shape, and distribution of the alloy carbides that are present in the microstructure. The function that these carbides serve can be understood through the use of analogy. The alloy carbides that appear in the tool steel microstructure serve a purpose that is comparable to the function of the wear resistance cobblestone. In the road, they provide a very hard contact surface area that is extremely resistant to abrasion and wear. In the heat treating high speed and tool steel, the high speed and tool steel intent for heating treating are normally prepared in a relatively soft condition with minimum hardness and maximum ductility, known as a spheroidized annealed condition. And in the powder metallurgy tool steel, as a result of pronounced ingot segregation, conventional tool steel and high-speed steel can contain a somewhat coarse, non-uniform microstructure accompanied by relatively low transient tough properties. The carbides segregation observed in longitudinal section of annealed M2 high-speed steel bars. And the cutting tool coating. In several cutting and machining applications, use in industry is not uncommon to surface treat high-speed steel and tool steel with application coating to reduce frictional contact, reduce thermal conductivity, and improve wear resistance. There are many surface treatment and treatment processes that are available. There are many surface treatment and treatment processes that are available. For example, it has been estimated that up to 60 to 70% of all carbide tools are now corroded. The surface hardness produced by a number of different types of coating is shown in here. So, thank you have been watching my presentation. I hope you all enjoy my presentation, and I will close with Om Santi 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Syallom, Namo Budaya, and good to see you all. Bye bye.